All right, thank you everybody for coming. So, as you know, we have a speaker from Carnegie Mellon, Joe Campbell, joining us today. He's currently a postdoc there doing research in explainable robotics, machine learning, and human-robot interaction. He got his PhD from Arizona State, working with Georgios Spinakos and Henny Ben-Amor. Before that, he was also at Arizona State for his bachelor's. So he's been working with Kadia Sakar, like I mentioned, at CMU since 2021, and has also been all over the place in terms of different types of travels, including National University of Singapore, Osaka University, as well as with different industry experiences. Actually quite jealous of some of those. Would love to chat more about them. Multiple-time author at ICRA and conference on robot learning, including and NeurIPS as well. And so today he's going to be telling us a little bit about explainable machine learning for robotics. So thank you for joining us.
Yeah, so thank you for the very nice introduction. Can everyone hear okay? Are we good here? Okay, all right. So yeah, today I'm going to talk about explainable machine learning for robotics. And before I start, I'm going to open with a short video clip, which is from a movie that inspired a lot of work that I'm about to talk about. So, do we have volume? So this is from the movie Big Hero 6. And the robot Baymax hugs the protagonist Hero from behind. And Hero doesn't expect it, so he's like, "What are you doing?" And Baymax responds with, "I'm trying to provide physical compassion and reassurance," and so on. And so this is a very idealized example, but it is illustrative of my vision, which I'm going to talk about today, which is I want to develop robots that are capable of explaining their actions to human users. So what is explainable machine learning, right? I mentioned it in the title of the talk. What is it? David Gunning, which was a DARPA program manager for the XAI program a few years back, he has this nice definition of it, which is it's a system that is able to explain its capabilities and understandings, explain what it has done, what it is doing now, and what will happen next, and disclose the salient information that it's acting on. And so there's been a lot of work done in other fields like psychology to actually more formally define what an explanation is with respect to humans. For the purposes of this talk, I'm going to stick with definitions that are commonly used in computer science, which is an explanation discusses what the agent is doing, what the agent hopes to achieve, and what information this is based on. And so why do we need explainability for robotics? The big answer is because machine learning models aren't perfect, right? So the world is very complex, especially if you're working with humans. They're very unpredictable. It's hard to collect samples, and the samples you do collect are often biased. So these models make mistakes all the time. And so as an example, I have two videos here from a hugging interaction from my work, and these are both driven by machine learning models. And so one of them succeeds, and one of them fails, right? So the one on the left, hug is good. The one on the right, for whatever reason, the robot doesn't release the person, and they're stuck. And then they have to awkwardly shimmy their way out of there. And so what causes one model to work and one not to fail, right? And explainability can help us answer this because it gives us transparency. It lets us understand how a certain prediction came to be. So with respect to robotics, there are two real implications of this. One is we can proactively determine if an action will lead to desirable behavior. And then two, if the behavior is not desirable, if the model makes an error, we can reactively improve the models through analysis, debugging, and intervention. And so the problem is that explainability is actually really challenging. There's this well-known phenomenon in the literature where there's a trade-off between a model's learning performance and its explainability. And by learning performance here, I mean things like model accuracy, training stability, sample efficiency. And in general, the reason this is because the more accurate a model is, like basically the more structured or interpretable a model tends to be, which means it's more explainable, means it's less able to explain complex data, so it's less accurate. So very broadly, there is this sort of negative correlation that happens between the learning performance of a model and its explainability. And so to date, we kind of have this, this notion that more complex models are less explainable. And which is a problem because especially in robotics, a lot of the state-of-the-art models are using deep neural networks, right? They're very performant, they're very capable. But at the same time, we can't explain them. They're complex, they're useful, but we don't know what's going on a lot of time. And so there's kind of a need here to develop models that fall in this upper right region of this graph. Basically, They're both performant and they're explainable. And so that's what I'm going to discuss in this talk. I'm going to discuss a few different approaches for developing these models. My work is all grounded in robotics for the most part. So you can see various applications of it here. And so the models and the approaches I'm going to talk about in this talk are particularly suited to these sorts of interactions. And so the question we ask is when we want to develop these models is like, it depends on what our application actually is, right? Because if we have, like, let's say a relatively simple task with well-defined features, we might prefer to use a probabilistic model. If we have a more complex task and we don't have well-defined features, then we might need to use a deep neural network, right? And especially the case in lately, we have pre-trained models a lot of times. We have foundation models and things like that, in which case we might still want to explain. And so we need methods for explaining existing models. And so that's what I'm going to cover in this talk. I'm going to discuss the approach for each one of these, and we're going to go in turn, basically. And I'm going to start with these probabilistic models. So in physical human-robot interaction, like this hugging interaction here on the left, it's a safety critical scenario, right? You have humans and you have robots and they're operating in close proximity. And this interaction may not necessarily look like it because it's a soft robot and interaction is relatively smooth, but oftentimes in HRI, it is safety critical. And so we want to be very aware of what the model perceives about the world and how it intends to act, right? We don't want to use a black box model like a deep neural network because we don't really know what's going on. Instead, we need full information, especially when a human is in a loop, of how the robot predicts the human will move and then how the robot is going to react in response. And so probabilistic models are actually really useful for this use case because now we can directly encode probabilistic relationships between human and robot movement, and then we can query the model and understand what's going on. And so by that, very intuitively, what I mean is we want to learn a joint probability distribution between the human and the robot joints. So if we look at the little diagram, we take basically human movements, human degrees of freedom. We take the robot ones and we throw it in a big probabilistic joint distribution. And this is an interpretable model, so we can query this model and understand these exact relationships and know how the robot will react based on how the human moves. And so very intuitively at a high level, the question we want to ask is, what will the human do and what should the robot do in response given observations and demonstrations of previous interactions? And this, by the way, this is just Bayesian inference, right? So I'll talk a little bit about how we do this technically in a few slides. But before then, I want to give an example of like, what are these explanations in such a model and how is this useful? So this was a tool that I had developed in my PhD. It's basically a visualization tool. And what it would do is each one of these plots represents a single degree of freedom. Basically, it's a joint that moves through space, right? So it model it for both the human and the robot. So the robot can be like arm joints. For the human, it might be position of hands and so on. And for each one of these, we have, the orange line represents what we've already observed in an interaction. And the blue line is what we expect we see in the future. And so we have basically trajectories over what we predict to happen for each one of these things. And we can, of course, turn this into a 3D representation and so on. But really, at the end of the day, what we have is we know exactly what we think the robot is going to do. And it's a probabilistic framework, so we can fully quantify uncertainty in a rigorous manner, right? In the upper right corner here, so this was actually approximate inference. So we have a Monte Carlo ensemble, but we can see the spread of the members represents uncertainty. And we also have the univariate distributions. We can quantify the uncertainty in each one of these. And so at the end of the day, we can understand exactly how we think the human and the robot will move and the uncertainty. So we can look at this when we're deploying the model. And if we see anything weird, we can either intervene or we can abort. And this basically gives us a lot more confidence in what we're doing. And so I'm going to talk a little bit about the technical details. I'm not going to get too equation-y. But really what we want to model at the end of the day is the state here. And in the state, we have robot degrees of freedom. So these are the control joints. So in a hugging robot, this might be things like the shoulder joint, the elbow, the arm, so on. And we also want to model the human degrees of freedom. So by human degrees of freedom, these are going to be the things we're looking at to respond. So again, in hugging, it might be position of the hands, the feet, what have you. And you can obtain these through like pose tracking with a camera, for example. And by the way, each one of these degrees of freedom, it's not a scalar point value estimate in time. It's actually the entire trajectory that we predict to see. And we achieve this by using a parametric model. You can think of it as something like a spline. It's not actually spline, but that's like a good approximation without going into details. And this will be relevant in like a couple slides. And then so then at the end of the day, we have our state. And what we want to do is we want to model a joint distribution P of S over this, right? And so now this gives us the joint distribution between all the human degrees of freedom and all the robot degrees of freedom. And so this is that joint distribution that I showed just a couple slides ago. And then the question we want to ask is, we have this P of S, we have this joint distribution, and then based on what we're observing the human do, we want to update our estimate, right? We want to say, well, okay, the human moved like this, so we have to update our estimate of what they're going to do in the future, and then correspondingly what the robot is going to do in turn. And this is just Bayesian inference, right? You're just conditional probability distribution, that's our posterior. And then we condition it on the observations as well as an initial state estimate, this S0, which is our prior distribution, and it's learned from demonstrations. In this example, it is. So this is actually like with this probabilistic framework, it's super sample efficient. So we're talking about learning demonstrations in dozens of samples, not thousands or whatever you have with a deep neural network. And then, so again, going back to this question, what will the human do and what should the robot do in response given observations and demonstrations of previous interactions? This is it. We just solve for this conditional probability distribution. And so this is basically recursion Bayesian inference. And we can solve it in many ways, usually using like forms of Kalman filters, for example. I'm not going to get into the math of how we do that, but it is very much a solvable problem. But there's one thing we have to consider here, which is so far I've been talking about degrees of freedom and movements as kind of spatial movements, right? But when you're talking about interaction with people, it's not just space, it's also time. If you do the right thing, but you do it at the wrong time, then that's still a failed interaction. And so we have to consider both of these components. And in a lot of prior work here with these sort of probabilistic models, space and time are always inferred separately, if time is inferred at all. And so what I'm going to show very quickly here is that we can infer both space and time jointly, and this really improves the applicability of this method for real-world use. And so to get some intuition behind how the spatial temporal inference works, this looks like what that trajectory, the spline that I just showed a little bit ago, right? And so this represents 1 degree of freedom in our probability distribution P of S. And so in order to update the conditional probability distribution, what we expect to see, how do we update it? We estimate what we're going to see, this blue circle, this estimated observation, and then we measure what we actually see, the green square. And this is our observation error. And we're going to use this error to tell us how we update this. The problem is what causes the error, right? It could be temporal error, because maybe where we think we are in interaction is not where we actually are. And if we move it either way, maybe we're a little fast, maybe we're a little slow, that explains the error. Or maybe our time estimate is spot on, and we're just wrong about what the trajectory is, in which case we have spatial error. And so in that case, we need to update the spatial components of the trajectory to reflect this. And so the problem is, how do we know whether it's spatial error or whether it's temporal error? This is why inferring these things separately is so hard. So the trick is when we consider multiple degrees of freedom at once. So I've added 1 extra degree of freedom here. It's just a simple line, but it also has an observation error. And the trick to this is to note that when we estimate time, this affects all degrees of freedom. We don't have a separate time estimate for every degree of freedom. It uses a shared one. And so this means we have a common error source if our temporal estimate is wrong. So this shared error source induces correlated observation errors. And then we solve for this correlated error. And then any remaining error then is due to the spatial error of the trajectories. So really at the end of the day now is we can do the spatial temporal inference very easily. We just plug in estimates of time into our state, and we solve them as latent variables. So here I represent it as phi, which is basically normalized time. It's 0 to 1 instead of 0 to t, for example. And phi dot represents how fast we're moving through time. And then, so now we have the red degrees of freedom, our spatial components, and we have these 2 phi's, these green components, and then we solve for them in a state. And now we have spatial temporal inference. And this actually greatly boosts the model accuracy. So to quantify it a bit, I'm not going to show many plots in this, I promise. But I did want to quantify it very briefly. So these graphs represent 3 different human-robot interactions. And the y-axis here represents the mean observation error across the degrees of freedom, basically how accurate our predictions are of what's going to happen. The x-axis represents how much interaction we've observed. And what we can see is that the blue line represents when we do the spatial temporal inference, and the red line is when we do it separately. So there's a huge decrease in error. This means the accuracy is much, much higher. And so the direct result of this means that now it's really applicable to a lot of different types of interactions. So this is that hugging interaction I showed earlier, but this time it's with a novel participant. So they didn't partake in training at all. And this is a purely adaptive hugging interaction, by the way. So the robot is responding to the timing of the hug when the person steps forward, the duration of the hug, the force of the hug. So it's reciprocating hugging force. And note the explanations up here. So whenever I would run these, you can't see me. I'm actually standing in the back here by the tables. I would always be monitoring these sorts of real-time explanations to see the distributions over and watch uncertainty and watch estimated force that the robot was going to use. And that way, even though it's a very close physical contact interaction, I can be sure of what's going to happen. And then so that was a collaboration with Honda Research Institute. And then I was like, oh, this is really cool. So I went back to my PhD lab and we had a Baxter robot. And I was like, well, can we still keep doing hugging? And so I bought a teddy bear costume off Amazon and we dressed it up. And we kept doing hugging. And we posted videos to YouTube. Because at the time, I was like, this is really cool. And then we got a bunch of feedback and people weren't so happy about it. So then we started doing other interactions. And so we have things like collaborative lifting of objects, and we did some dynamic throwing of stuff with balls. This one is interesting. So this is actually a shared control problem with the lower limb prosthesis, where we were trying to like actuate the prosthesis to avoid like dampening forces, which can cause osteoarthritis. And in the handshaking one in the lower right, it looks easy. I promise it's not, because that's a musculoskeletal robot. It's pneumatically actuated. So the dynamics are extremely nonlinear, but we're able to still do some cool things with it. So really what I wanted to indicate with this part of it is, these sorts of probabilistic models, they seem like simple tools, but they're actually really powerful for certain types of interactions, right? So depending on our interactions, if they're relatively simple and we have our well-defined features, we can get really cool things out of it. But that's not always the case. And then so next I'm going to talk about what we can do when we need to use deep neural networks. So, the probabilistic models that I just talked about, they're really good for these sorts of simple interactions with clear defined features. But, what about interactions where this isn't the case? So for example, this multi-robot coordination problem here. So there's two teams of robots, and it's a competitive cooperative scenario. And we end up with these sorts of very complex interactions that happen, these sorts of robot-robot interactions. And so in this case, we might want to use a deep neural network, right? Because it can implicitly learn features. We don't have to define them. And it can sort of enable this sort of complex decision-making that enables these complex interactions. So when we use a deep neural network, how can we explain it? How do we know what's going on? Because normally, while they're performant, they're very opaque. We don't know how decisions are made. And so that's what I'm going to discuss here. Before I get into that, though, I'll give a little more information on what this setup is. So this is a multi-robot competitive cooperative game, and we have two teams of robots. So we have this team of the orange robots, which are attackers, and they basically just need to reach this blue circle, this goal. And then we have the green team of robots, which are defenders, and they need to stop them. And they have this equivalent of like a laser tag. They have a ranged tag that they can use to basically make the attacker robot sit out for this round. And what we end up is, so this is trained with reinforcement learning, and we end up with these sort of very emergent complex behaviors, right? So we get things where the attackers might employ deception, and where defenders can employ defensive strategies. And so traditionally in deep learning, the way people would explain these sorts of networks is by using things like feature attribution, right? So explain it just in terms of simple combinations of input features. But that's not as sufficient to explain complex behaviors like this. So one way in which you can do that is to describe these things as abstract concepts, right? So we say, okay, each one of these attacker strategies is a concept. And another concept might be target priority, like what is the highest priority agent for me to stop, and is opposing agent within range, for example. And this is all with respect to the defenders, by the way. And then if we define concepts in this way, let's consider agent D1 here, which is moving forward and tagging agent A2. And then we can ask, what concepts did D1 use to inform its action? And then it's a relatively simple example. So we can get an answer like, oh, A2 is a high priority target. It's within targeting range, and it's attacking from the south. And so this is kind of a very nice, useful, high-level explanation that describes the behavior. So then how can we generate explanations using this? One way is to use concept policy models. And so what these are is they're basically deep neural networks where we encode these concepts in the latent space of the network. So what I have here on the bottom is this is a kind of simple toy example of a deep neural network, right? Two hidden layers, input, output, fully connected. And then what we do on the right now is we basically split it in half, and we inject this bottleneck layer in the middle. And so each node in this layer corresponds with one of these concepts. And so, for example, we have a concept for strategy, for example. And so one of these nodes will correspond to a strategy. And then ultimately what happens then is the layers of the network that are upstream of this encode these sort of high-level features, these concepts. And then the layers downstream use the concepts in order to produce robot actions. And then at test time now, what we can do is we can actually just query these nodes. We can look into them, see their node activations, and we can understand what concepts the robots are reasoning with. So to give an example, this is that same interaction from before now, but with the concept node activations. And we can visualize them. So you can see here, like this is from the perspective of the defending agents. They're visualizing, oh, I'm targeting A1 and so on. I'll wait for it to loop around here. So you can see we're targeting A2, tag A2, and you can see it shift in real time to targeting A1, right? And you see it also predicting that the agents are going to attack from the south and so on. And so this is a very useful explanation. So again, I'll give a little bit of technical details for how we do this. As before, we want to estimate some state, right? So in this case, the state, again, contains the robot degrees of freedom. So in this example, it's just a simple differential drive robot. So it might be things like wheel speed, for example. And given a sequence of observations, then what we want to do is we want to predict these states. Again, it corresponds to control degrees of freedom. So these are going to be actions we issue to meet these states. And so it's there's no probability distribution like before. So it's input-output mapping from a deep neural network. So observations in, states out. And the trick in is how do we learn the concepts in this middle layer? In this work, so we learn it with supervision, right? So this means that we need labels in order to learn these. So if it's a categorical concept, it's a classification problem. If it's a continuous concept, it's a regression problem. But we need to learn and encode these in these middle layers. But this is a problem, right? Because the advantage of deep neural networks is we don't want to fully define all the features. Oftentimes, we don't know what they are, especially in these complex things. And so this is an issue because the blue nodes, the downstream nodes, the only thing they're taking as input right now are these concept nodes. And so if we don't sufficiently define them, that's not enough information to solve the task. So as an example, let's go back to these kind of 4 concepts I defined previously. And let's suppose, for the sake of simplicity, we issue 2 of them, strategy and priority. So we have our observation go in, our network predicts these 2 concepts, and then those go to the downstream policy, and we predict the action. So in this case, our running case with D1 here, D1 is like, okay, agent A2 is my priority, and it's attacking from the south. Great. It doesn't know where A2 is. This isn't enough information to solve the task. How does it know where to turn and where to go? And so in this case, it's insufficient information to actually perform any action, right? So we have an incomplete concept set. And the way we can get around that is by injecting additional nodes into our concept layer now. And these are not constrained by supervision. So these are unsupervised concept nodes. And so the purpose of these is that they can learn any additional information needed to solve the downstream task. And so to quantify this a little bit, here's some win rates from 2v2 and 3v3 games from real world runs. And we can see that when we do have an incomplete concept set and we introduce these unsupervised nodes, they basically double the win rate, right? From the perspective of the defenders. They go from 23% to like 51%, and similarly 3v3. Another quick interesting thing is that when we introduce concepts in general, so we have the same architecture, just minus the concept supervision, they improve the win rate by a lot, just by the presence of the concepts. And the reason being is because these concepts encode complex behaviors, which may be difficult to learn through standard reinforcement learning, right? And so we're basically giving supervision, we're giving regularization to say, hey, these are important behaviors to understand and learn. And just by giving that information, it boosts the win rate by a lot. But there is a catch, there's a problem. Because we don't know what these unsupervised concepts are learning, right? So in which case, they could learn redundant information. So let's suppose we have a supervised concept, which learns a strategy-related information, and the unsupervised one also happens to learn strategy-related information. In this case, the downstream node might choose to only use the information from the unsupervised concept, right? It might ignore the supervised one because it's redundant and doesn't need it. But our explanation is derived from the supervised concept. So now we have a problem. When this information, when these predictions match, so they both predict go top, it's okay, there's no problem. Our explanation is correct. But when they don't match, let's suppose the unsupervised concept predicts the agent goes to the bottom. Now we have a problem because now the downstream layers are going to use the information that says the attackers are going to the bottom, but our explanation tells us it's using information that goes to the top. So the information that we think the network is reasoning with is not actually what it's reasoning with. And so in this case, what we want to do is we want to force these unsupervised concepts to represent different information than the supervised ones. Essentially, we want to disentangle their learned representations. And one way we can do this is by minimizing the mutual information between the supervised and unsupervised concepts. And by mutual information, it's, a standard definition is the amount of information that you obtain about one variable by observing another. So if we minimize this, then knowing the unsupervised concepts tells us as little as possible about the supervised ones. This means that they encode different pieces of information. And so to quantify this a little bit, I have 4 benchmark data sets. This isn't a robotic data set. It's a vision one, but it's useful for evaluation. And what we've done here is a classification task. So the accuracy is on the y-axis, and the number of these unsupervised nodes that we've added is on the x-axis. But we've done one caveat here. We basically, normally, the predicted supervised nodes are used by the downstream layers, right? But now we've randomized them. We basically said, okay, you don't get the predicted ones, you get random noise. The idea here being that if the unsupervised nodes encoded redundant information, accuracy won't drop that much because it still has information it needs. But if we've disentangled correctly, then we expect to see a big drop in accuracy, which is what we see here. So red is when we perform this mutual information disentanglement, and blue is when we don't. And we can see that in general, even across large numbers of added unsupervised nodes, we see this drop in accuracy, which is what we want to see. This means that we've disentangled representations and our explanations are more faithful now. And so the end result that we get is we still get high-performing policies here. So these are a bunch of, we have hours of these, of the emergent behaviors that we've learned. I only took videos of 2v2 because 3v3 tends to, we have a little relatively small space and it runs into walls a lot. But we get very nice behaviors out of it. I did not annotate the concept activations because it's time consuming, but we do have access to all of them and we get very nice explanations. So what I wanted to convey here is, we can learn these sorts of semantic concepts in a deep neural network. It does not give us full transparency, but we're starting to peel back the layers a little bit. We basically say, at this point in a neural network, I know what information is being used there. And I don't know how it's being used afterwards, but I do know what is being used. And so that's very important, I think, baby steps towards the way of transparency. And so lastly, I'm going to talk about then some model agnostic explanations. And what exactly does that mean? Concept policy models and the probabilistic models are very useful, right? The problem is that we need to learn the model. We have to encode them in the model structure. The concepts are supervised, right? And so what happens if you want to explain an existing model? We might have a pre-trained model that already has pretty good accuracy, or you might be using a foundational model like CLIP or whatnot, in which case we can't edit the model structure. It's already fixed. And so one of our goals then to use these pre-trained models is we want to explain black box models using only observations of the robot's behavior, the inputs and the outputs, because we don't care what the model is at that point. And large language models, they're very popular. I'm sure most of you might have used it in ChatGPT. So they're very capable of doing this sort of high-level common sense reasoning. And what I'm going to talk about is that we can actually use LLMs to explain black box models in this fashion. So the way we do that is we want to use an LLM to do common sense reasoning, right? So we have a robot model. We have this orange box. It doesn't matter what it is. It can be deep neural network, it can be probabilistic matter, whatever. All we know is we have an observation going in and we have an action going out. And what we want to do is we want to take this observation and action. We want to give it to an LLM and we'll say, hey, explain this. Why did the robot take this action with this observation? And it is an LLM, so we are going to get a natural language explanation out, which is useful because more and more these robots and these agents are being used with, in the public with lay people. And so natural language explanations are inherently a little more accessible. And I will talk about that a little bit because we did run some participant studies. So the scenario that I'm going to represent this in is we want goal-driven behavior, right? And so we have this simulated search and rescue task where we have a heterogeneous team of agents. So we have a blue agent, which is an engineer, and it needs to go around, explore the environment and remove rubble. And then we have a red agent, which is a medic, and victims might be trapped under rubble. So after it's removed, it can heal them, it can rescue them. And it's partially observable, so we do need to explore. And so it's an example of different behaviors. So here I have the engineer moving, and it moves to that square up there, and it has 2 options, right? One, it can go south and join its little medic buddy, or the other is it can go to the right and continue exploring the environment. So we have different types of intents and behaviors that can arise. And I know this isn't physical, real-world robots here. Part of it is because for ease of experimentation, and another because it spun out of a DARPA project on search and rescue, and this is our test bed. But the results I'm going to show, I do think have great applications for real-world robots. And so to give an example of what these explanations look like, so I want to explain that previous example with the engineer. So let's say it moves from the top, moves to the right, the solid blue arrow. Ultimately, it moves to the unexplored room, that 30 on the right, dashed arrow. We don't know it at the time. I'm just giving you this information. And so what we want to explain is that first initial solid blue move. And so I gave this information to GPT-4, and I said, explain this action. And we get this natural language explanation over here on the right. And we can see a couple of things. One is that it identifies the agent goal, right? Moving to 20 positions the engineer closer to room 30, because it is where it wants to move, so that's good. Then we see the rationale, it goes there because room 30 hasn't been explored yet, but most of the surrounding rooms have. And then finally, it even identifies the strategy. So it suggests that the engineer is prioritizing exploration of unexplored areas. And so this is kind of a simple example, but we can see that the LLM is very capable of reasoning over this sort of goal-driven behavior. And also, if you remember back to the very beginning of the talk, so I had 3 pieces of information and an explanation, right? This corresponds to that. So now we come full circle, and those pieces of information we can explain here. The problem is that we can't actually just give an observation and action to an LLM and get an answer. Part of it is because LLMs are pre-trained over internet scale data sets. They're very good for general purpose reasoning. So if I ask a question like, hey, the robot found a person trapped in the rubble, what will the robot do? Then we might get an answer like, well, the robot's task is to find and rescue victims, right? So of course, it'll work on clearing the rubble. And this is a very reasonable response. This could be something that could happen. The problem is we don't want just like a possible explanation. We want an explanation for that particular model, for that particular robot. And so what we need to do is we need to take into account the prior behavior. Like what if previously that robot basically fully explored the environment first and waited to take any action like removing rubble until the very end after it located all its victims? In which case, we would want to provide this information, and then we expect it to be reflected in the explanation, right? So the robot seems to be following a strategy of first exploring the environment. And so I'm going to refer to this as behavior condition reasoning, because really we want to condition our explanation on an agent's existing behavior. So the simple way to do this sort of reasoning is to just collect a pile of previous observations, right, of robot behavior, and we inject it into the prompt, and then we query like normal, and we say, hey, why is the agent taking this action, given its historical behavior and whatnot? The problem is that this doesn't actually work very well. It leads to a very long context window. Depending on how complex the behavior is, you might need to put a lot of observations in there. And unfortunately, LLMs currently are not good at accurately reasoning over long horizons. So you get hallucination. And by hallucination, I mean the presentation of false information as fact. If any of you have used ChatGPT, I'm sure you've encountered this before. They even have like little warnings plastered everywhere. And in the context of explainability, this is actually a really big problem because ChatGPT is very good at presenting information like it's accurate. But in the case of explanation, it's now not, right? So you're looking at this and you're like, oh, great, it's real. And you have an overconfidence issue. You trust this explanation when you shouldn't be. And so really what we want to do is we want to take the prior observations and we want to have some sort of transformation into some representation that is more LLM comprehensible. And by LLM comprehensible, I mean it's more compact, it's easier to reason over, and it leads to fewer hallucinations. And so what we found is that decision trees are actually really good representations for this. So we take that pile of observations, we train a decision tree over it, and so now basically what we're doing is we're distilling the agent's policy to a tree, and for this given observation and action when explained, we go to the decision tree, we extract the corresponding path. So this is the ordered set of decision rules that could have led to this action, and then we give this to the LLM instead. And so now, instead of the big pile of observations, we give it this path, and it's more hierarchical, right? It's a hierarchical order set of decision rules which indicate feature importance. And intuitively, the reason this works is because when we give a big pile of observations, we're basically telling the LLM, hey, there's some useful information in here. There are some features here. Go find them, figure them out, and then reason over them. But with the decision path, we've already done that part. We're basically saying, hey, here's some candidate features that might be helpful in explaining behavior. Now try to reason over these at a high level. And the result is that it works much better. So we had some poor undergrad student go through and manually quantify the hallucination rate. So we had sampled a bunch of behaviors from, I mentioned before, there were kind of two different strategies. So prioritizing rescuing victims versus prioritizing exploration. And we generated a bunch of behaviors. And what we see is that explanations generated this decision path result in way fewer hallucinations, like more than 2 times fewer hallucinations than with the pile of observations and no conditioning at all. And then correspondingly then, again, the same poor undergrad student had to go through and look at the explanations and see whether the information was actually accurate. Because we know the ground truth, we know the actual goals and the strategies for these behaviors, and we would manually check these and see if they correspond, and they do. And so what we see is these lower hallucinations do in fact lead to more accurate explanations. So then the question is like, okay, we have accurate explanations. Are they useful? And we ran a relatively simple participant study where we generated a bunch of behaviors, observations, and actions. And then we basically presented pairs of explanations to each person. Or like, which one do you prefer more for explaining the behavior? And so one of them was the explanation, so the decision path. Another is with the pile of observations. And then another one was like a baseline with language templates. And far and away, the participants preferred the decision path explanations. They're more accurate, they're more representative, they're more useful. One of the interesting things is we also had human domain experts come in, full knowledge of the policies, and write down natural language explanations. And there was no preference there. So people did not prefer the human ones any more than these LLM-generated ones, which is pretty significant, I think. And the last thing to note here is we're using an LLM, right? So we have a dialogue window. So normally we start this off by querying the LLM for an explanation. So you get this sort of explanation which describes the strategy and the goal and so on. But then what we can do is we can keep going. We can keep asking follow-up questions and contextualize this. And so what we did is we would turn basically a chat window over then to a person. We say, hey, you know, if you're interested, you can ask follow-up questions. And this is an actual interaction that we had. So then we found a person that said, hey, what do you think the engineer will do next? And so this is basically next action prediction, right? If we are able to effectively reason over the agent's goals and intents and so on, then it should result in predicting future behavior. And that's exactly what we see. We see based on the current pattern behavior, it is likely that the engineer will continue moving towards the rubble in room 3-3. So again, this perfect behavior condition behavior. And then next we saw him ask a counterfactual, basically a what if question. So what will the engineer do instead if there's rubble in 2-1? And so again, we get a very nice response. If there's rubble in room 2-1, it might change its course and move to there because it's closer than its previous goal, which is in 3-3. And so perfect. But then we wanted to ask one more thing, which is, okay, is this sort of interaction actually helpful? And we found an interesting thing. So humans have this sort of bias. We have mental models of anything with agency. We basically assume an agent or a robot will act in some certain way. And in the case of this, humans typically assumed agents would act according to prioritized rescue. It's search and rescue. Why would it not rescue the victims? And so this is kind of expected behavior. And so what we found is that, you know, when the agents executed this behavior, people were like, oh, it did what I thought it did. I don't need to interact. I know what it's doing. When they prioritized search, this was unexpected to most people. And they're like, why is it doing that? And in that case, they found this sort of interaction much more helpful. And so this kind of confirms, you know, previous research that has looked at this in different ways. But it's a really interesting observation to note here. And so, yeah, what I want to say here is that, you know, there are lots of times where we have existing models and we still want to generate explanations. Do nothing, like we want to get something out of it. And so we can start using these big pre-trained models and we can get some really interesting explanations out of it. So very quickly here at the end, I'm going to discuss some potential areas for future work, which by the way, if anybody's interested in this, let me know, potential collaborations. So what I've talked about so far are explanations in the form of trajectory distributions and abstract concepts in natural language. One thing I have not discussed is multimodal explanations, right? So it doesn't have to be one or the other. We, you know, especially with robots, we have lots of sensors and lots of things like that. We can have cameras, we have microphones and speakers, so we can use vision, we can use language and speech. And an interesting one is action. So robots have agency. They can take physical actions to elucidate behavior. So in this case, this is a very contrived example. I just put a pepper robot in front of my office and a chip bag on the ground. And even without sound here, you can see it points to the chip bag, points to the trash can. This is very explanatory behavior, right? And similarly, there's been a lot of cool work on things like, augmented reality now, which I know Brad is doing a lot of, but we also have like image projection. So this was an old example at my old lab where we were projecting like directions and intents and things into the environment, but this can very easily be used to project explanatory information. And so really what we're gonna think about is like each modality of explanations can convey different pieces of information. And so when you give all of them, it get kind of more aggregate, information and a better understanding of robot behavior. Another one is personalization. So I presented these natural language explanations, right? And it's all about making accurate explanations. But explanations are really, conditioned on beliefs and knowledge or social interactions. So for example, what does the user know? And do they need context to understand the explanation I'm about to give them? And can a robot ask proactive questions and to gauge this context? So for example, here's a collaborative example here where maybe the robot and the human are lifting this box and the robot's moving very slowly because it contains fragile items. In which case the human might be frustrated and be like, hey, what are you doing? So in this case, the robot knows that the human doesn't notice fragile items in there and be like, oh, I am moving slowly because the box contains fragile items. So this is useful, right? The hard part here is actually understanding what the human knows and what they need to know to understand explanation. But I think there's a lot of really cool work in this area, especially in like basically artificial theory of mind, trying to infer what the humans know. And we have some interesting work in this area ourselves. So I think this is a promising direction. And lastly, I didn't have time to talk about it, but so far in this work, it's been a lot of explanations for transparency, right? Understanding models. There's a whole flip side to this though, because explanations tell us the decision-making process. And then we can do more targeted interventions so we can improve the models better. So for example, we have some work with the concept policy models where, when you're querying these nodes and you see it's incorrect, you can intervene and you can set the correct value for that activation. And then you can propagate it forward and you get sort of this local correction because now you affect the immediate output. Or you can propagate it backward and have sort of like a test time gradient update. And so there's tons of interesting directions to go here, right? Can you make it sample efficient enough for lifelong learning? What happens if you give explanations for an intervention to generalize it in the future and kind of get self-correcting models? So I think there's sort of like explanations for learning, transfer learning, one robot to another. Lots of interesting things to do here. And that's it for me. Like Chris mentioned at the beginning, I've worked at a lot of different places over the years, and none of this work would have been possible without all my collaborators. So yeah, that's it for me. Thank you.
Questions? Yes.
Yep. So going back to the problem on explainability, right? So when we choose the unexplained or unsupervised nodes. So I'm assuming that the network is pretty much like auto-encoded, right? And then you have responsive nodes in between, and that's trying to learn the representation of the encoded file. And then you have this unsupervised node. So I'm curious about like how is the training strategy for that? Because if you're using like normal gradient descent already, that then you're going to learn the final layers, right? But then how is this unsupervised nodes learning these?
Okay, so the question was, is it like an autoencoder setup, and then how do you learn these? How do you have these multiple losses and learn these downstream nodes? Exactly. So it's not actually an autoencoder setup. Think about normally if we were to have a neural network for continuous control, and then you have observation in and action out. That is our setup. And then what we do is we insert concepts in the middle of it. So there's no autoencoder side. We're not reproducing the input. We are producing separate output. But your question as to how we do this sort of supervision, we actually just add an auxiliary loss. So we have an objective function, right? Normally that'll be in reinforcement learning, it'll be maximizing whatever your reward is. And then what we do is we add this auxiliary loss onto this objective that says, hey, but also minimize accuracy of the concepts. And then that's all we do. And then actually, when we have the unsupervised nodes, we add an additional auxiliary loss, which says also these extra nodes, unsupervised nodes, have to minimize mutual information here. Yeah. So, there's just to kind of maybe preempt here. One of the difficulties here is like, how do you define the concepts ahead of time, the supervised ones that we have? So, for the sake of this work, we had manually defined like interesting behaviors that we saw coming out of the policies. And then you have to, again, maybe you have a poor grad student that's doing like a semi-supervised, label a few of them, bootstrap it off and so on. The other interesting thing is having some way to automatically label concepts. So we have some really interesting work coming out with like neurosymbolic models where we'll learn big knowledge graphs of existing like generalizable concepts from things like visual genome, for example. And then now these concepts, instead of being a layer, it's actually a whole knowledge graph in between. And so that's like a really interesting setup to avoid having to specify them. Yep. Yep, it's you. Yep.
So you're using basically the previous action and next observation.
So this is not the previous action. It's actually the current observation and the current action that results from that, because we want to explain this current action.
So there is no mechanism there that
right. So yeah, and you hit on a good point here. So like, how do we guarantee the faithfulness? Unfortunately, we can't guarantee it. Like the point of that work was to try to do what we can to minimize hallucination, which by extension means we're improving faithfulness. But that is for sure an outstanding problem with this. We've been playing around with future things like, oh, can we use different representations other than decision trees, right? Because decision trees are also kind of limited in their expressivity. So can you have things like random forests? Or can you have like gradient boosted trees? Like things that are more expressive and maybe harder for humans to understand, but still parsable by LLMs. So I think there's potential there that further reduces hallucination. And then of course, yeah, there's gonna benefit from all the other works in LLMs that are also trying to tackle this problem. So yeah, unfortunately, like we made progress, but it's not solved yet. Actually, I will say real quick, one thing that is also really interesting is, so I talked about, really, I didn't describe it in detail, but there's kind of two competing themes in explainability. One is using an inherently interpretable model. So that would be things like the concept policy models and the probabilistic models. Like basically, we look at the models and understand what's going on, like interpretability. The other way is to do the last section, the model agnostic ones. In this case, we're not looking inside the model. We're just trying to explain it from the outside. I think in the future, combining these things is a very promising direction, right? So related to like, how do we guarantee the faithfulness of an explanation? What if we have some transparency, some insight into the model of concepts, and we can use that to further guide the faithfulness of the explanation? And then there's all sorts of other interesting things with robots, like, because you have agency. So, a lot of times with these explanations, you might generate like 5 of them with an LLM and then check for consistency. But like with a robot, you can also like take an action and then generate another explanation and see if that's consistent with what you previously estimated based on the action you took. So all sorts of different things we can try in the future. Yep.
Probabilistic approach for taking action off of a sample space of human interactions. But what do you do when the human doesn't act at sample space? How does it generalize?
I love this question. Let me see if I hope I have my, oops. Oh, sorry, I accidentally killed my presentation somehow. Okay, so this is, oh no, wait, this is the look ahead one. Nope, I don't have it. But I had a, gosh, I want to follow up with you later because I have a fun video showing we were testing exactly these edge cases, sort of things like what happens if the human does nothing and you introduce artificial delays and all this other sort of stuff. And we get really nice adaptive behaviors because we're estimating time. So if the human does nothing, time doesn't proceed. And so the robot also does nothing. Or likewise, if there's a delay, at first the robot does nothing, and then the robot will take actions. And actually, since we're already on this slide anyway, one interesting thing I want to point out is the probabilistic models, we can predict what's going to happen in the future, right? So when you're dealing with robotics, you have all sorts of issues like time delays. You have control lag. You have the time to get the observation, perform your inference, and then send it to the control and actually execute. So there's this big temporal lag, and it's going to create kind of mushy feeling interactions. But with the probabilistic models, what we can do is instead of reacting to what's happening now, we react to what we predict will happen in the future. And we can basically counteract this lag. So like this is referred to as a phase lag. And so even 5% ahead, look ahead, like way more smoother behavior. So the probabilistic models gives you lots of fun things like that too.
Other questions? Well,
how to understand the policy network code? From what is, as far as curious, how you prescribe a concept to a neural network node? Do you look at the output and the respective activation? And that's how you do it?
Yeah, so basically you treat it much like a classification problem, right? So like, let's say, for example, let's say we have 4 different strategies that might occur, right? And these strategies are mutually exclusive, for example. In that case, we would have, much like a classification problem, we would have one node for each strategy then, because and that corresponds to, you treat it like a multi-label problem, basically. And then so what you would look at the activations for each one of these then, and then pick the one with the highest, let's say, activation. But of course, the relative ordering of them also indicates some uncertainty. But you can basically think of all those internal nodes as being treated as either classification or regression problems, respectively, like in a group-wise fashion, because you only look at the nodes within each concept. And then the separate concepts you look at separately. Does that kind of make sense?
Yes. Could you guys figure where 2 things are activated? So let's say there's a linear or non-linear combination of those resulting in one of the behavior. Because it's an inner node, it's not the outside node.
Well, we do have, I mean, at the end of the day, it is a supervision problem, right? And so we do specify that, like, hey, this state exhibits this concept. And then we minimize the loss to predict that concept from that state, for example. So it's not that, you know, the different concepts are combining necessarily. Actually, are you asking about like the output of the model? Like, is the output driven by multiple concepts?
Yeah, so I'm trying to understand how you can ensure that one node restricts itself to one concept and not a combination of those inner concept nodes.
Oh, I mean, simply by supervision loss. Because I mean, if you minimize just supervision loss for that concept, then by definition, you will only try to be predicting that one, right? Yeah. Yep.
So you first
Yep.
This is more like a question. Where do you see, I guess, the network? Yeah,
Yes, so I have not, but like, I mean, that is of course a valid scenario, right? The action, like the behavior is information gathering in and of itself, right? So we did not encode that specifically. Well, I mean, actually we kind of did in a sense, like prioritizing exploration is information gathering. We're trying to understand what is in each room, whether it be rubble or victims or whatever. So in some sense, you can see that whole, in like the model agnostic stuff, the whole prioritizing exploration one where the engineer ignores going to the rubble and the victims to explore environments. Like that in some sense is information gathering. Yeah.
Explicitly telling this kind of happening, right? It's an implicit information gathering.
Maybe. I actually don't think it'll be hard as you think though. Because like, let's say, for example, you know, in this simple case, we have an environment that is partially observable and there's no, let's say we don't have any rubble or victims available and whatnot. So in this case, like implicitly, there's no obvious goals. We know the agent must be taking exploratory actions at that point, right? To explore more of the environment. Now, of course, you can get more complicated beyond that because you can have, like, for example, maybe a goal is visible, but not in full. Like you might have to gather more information to figure out how to handle that goal. For example, in the search and rescue one, we actually had a much more scenario later on because it was DARPA and they were like, what if we had bomb defusal? And then so we had this complicated thing where like you had to figure out what kind of bomb it was before you defuse it because otherwise the agent blows up. And so that's a perfect example then where even though you found the bomb, you have to take more exploratory actions to understand what to do. So you can still explain that stuff. Like it does get a little trickier depending on the complexity of the task for sure, but I do still think you can explain it.
So let's say you start. You actually visualize that. Find the policies that I don't know where the target is, that I have to take exploratory action.
So in the concept of the participant study we ran for the search and rescue, what we would actually show the user is we'd show them the current state, the current action, and then the agent always had some, so like whatever future goal. So that the exploration was kind of implicitly involved in that. And so actually in that case, I had in my graph, I had this sort of, I don't know if I'll be able to get to it now. So one of the behavior types that we had was denoted as ambiguous. Here it is. So here, so this ambiguous goal. And so that represents exactly the scenario where like we don't actually know fully what the future goal could be. Like the agent's action could be one of multiple things because there's not enough information to tell. So we did represent that in the participant study. Like you don't really get, like there is some noise depending on whether people are satisfied by that explanation or not, but we at least did account for it in a participant study. Yeah. Yeah.
What information did you use here element context of your requirement? How much is too much? How much is too little?
Yeah, so that's a good question because part of this is you do have to describe the MDP basically in natural language. And you're very right that so LLMs can be biased very easily by contextual information. So you do want to avoid giving too much information. Like if you say, you know, even some simple things like, oh, this is a search and rescue task. The agent's primary goal is rescuing victims. Like that's going to bias everything towards this sort of prioritizing rescuing, right? So I don't have like a great rigorous answer for you. We tried to have a minimal task description that conveyed enough information to reason about the task without biasing. So we do have, there is an archive preprint up. We have follow-up work on this that's currently in review. I can maybe follow up with you and send it offline. That has like in the appendix, for example, we have descriptions of these things. Yeah, like unfortunately, I think right now, especially in the wild world of LLMs, there's no great like, what's a systematic way of defining these things? It's just, yeah. Yep.
Any last questions?
Yeah, I was wondering about the scalability concept.
Yep.
So more complex settings such as the gate. What if I decide to, sacrifice myself to let my whole team win?
Yeah.
That kind of concept.
Yeah. So you raise an actually really interesting thing because there can be hierarchies of concepts, right? Like later, these more complex behaviors might actually be combinations of earlier concepts. So the thing with the concept layer is I only describe models in which there's one concept layer. You can insert more than one. You can insert one downstream with a different set of concepts, for example. And that's totally fine. You just add another auxiliary loss into your model. So things like that you can describe. But as with all things with architectures, it's a little bit of trial and error over like how many layers down does it need to be and this sort of stuff. But you can do it.
Well, I think we're out of time, so let's thank Joe again.